Okay, so let's start with this notes that I sent you. So I guess I just hope that at least here everybody is fine up to here, up to equation 4. The derivation was given last time. So now about this exercise, how many people were able to do it? It's actually just 2 lines, nothing much here.
Just applying
Sorry,
the
Lalu.
state to side T. Just apply like left hand side to a state and right hand side to a state and see that you'll get the same answer for all states. Like psi of T3 on the left hand side of
No, I
operators will be.
just wanted to see it as an operator identity. Okay, so
If it's true for all state, it'll be an operator identity, right?
yeah, that's true. But how do you show it is true for all states? You want to show it somewhere from this definition, or?
No, sir, you can't you like by definition u of T1, T3 to psi of T3 will give you psi of T1, right? On the right hand side, if you apply u of T1, T3 to psi of T3, and even on the left hand side, apply to psi of T3. So left hand side.
Yeah, you are saying that if you act on a state at psi
Yeah,
T3,
yeah.
it
It'll
will
just give.
translate to T2, and then
Yeah,
and then when
like
you
by
apply it again, it will
definition.
go T1. Yes, that's right. Yeah, and that's true for all states.
Yeah.
And it will be true. Yeah, certainly that's the correct way of proving it. That's excellent. That's the correct logic because it's true for any arbitrary state. Okay, but what we could also do is as follows, that we could also try to see it as an operator identity in a bit. So actually, Kabir is quite right. I would show this whole section, I would show a very simple like 2-line proof, which I took a lot of time here. And I will also do the same here. I mean, what Kabir just proved in 0 line, I would give a more laborious proof. And the idea of this laborious proof is simply to see some interesting stuff which is useful in other contexts. Okay. So has anybody tried proving this as an operator identity just by taking this as a definition and multiplying
So
these
I
two?
tried actually. I first did that only, and then I was like, okay, there must be a shorter way because you said everything can be solved in like 2 lines. And then I
Yeah, even
realized.
this one is 2 lines actually.
Okay, it took me a little longer, but I think.
Yeah, but Kabir, you're absolutely right. I mean, your proof is as good as anything. I mean, that's the correct way to do things. In fact, these are the things that I would be talking about today. How to, but let's see it a little bit in a more dumb way. Okay. So let me stop sharing and go back to the. Okay. So today it will be a little bit inelegant because I have to do this back and forth switching. Sorry. So let us see in the little bit dumb way then. So we know that you. Okay, this is what we know. And we also know, say, U T2, T3 is this. And all of these are integrated from minus infinity to infinity, or sorry, in this case, from T2 to T1. In this case, it will be integrated from T3 to T2. And then you have time ordered m factorial h bar to the power m and m factorial h t1 tilde to h t to the m. Okay, so now if we multiply these together, we have to show that you get u to t1, t3. So let's multiply this together. So u t1, t2 times u t2, t3 would be then sum n m, and then you have minus I to the power n factorial n minus I to the power m factorial m and h bar to the power m, h bar to the power n. And then you have then dt1 to dtn and dt tilde 1 to dt tilde m, and time ordered of these two things, ht1 to htn, and time ordered of ht tilde 1 to ht tilde n. So these have to simply rearrange now in this. I have to rearrange all of these things now in this as a ut1 t3. And so what I would do something simple. So first observation is that if I take time ordered product of say O1 T1, O n Tn, and then time order product of say O1 T tilde 1, sorry, let me call it O tilde T tilde 1 to O tilde M T tilde M, something like this. So important thing is that here T1, all of these sets T1, T2, Tn, all of these times are greater than this set T1 tilde T tilde M, right? This is true here, that all of these times are greater than these times, right? Because this is T1, T2 and T2, T3. So T1 is greater than T2, greater than T3. And these integrals go from T2 to T1. All of these go from T2 to T1. And all of these integrals go from T3 to T2. So all the arguments that are appearing here are lying between T2 and T1. All the arguments that are lying here are between T3 and T2. So basically all of these times are greater than these times, right? So then we could simply write this as time ordered of all of these things put together. Right, because here it is time ordered, and so I can put the time ordering symbol as a whole, right? Is this part clear or not? Yes or no?
Yes, sir.
Okay, if it is clear, then what I can do, I can rub this out. So then I can replace this whole thing with.
So will there be no multiplicative factors? Like if you put the whole time ordering to the whole thing, there should be some multiplicative factor that comes, right?
Because no, there is no multiplicative factor because there is only one ordering here. So because all of these stuff was greater than this stuff, there's only one kind of ordering. You are not choosing anything here. Wait, I will. There is no multiplicative factor. Why do you think there's a multiplicative factor? So if I have, again, if I have TA T1, BT2, and something like T CT3, D TT4, and both T1 and T2 are greater than T3 or greater than equal to T3, T4. If that is the case, then I can simply do a time ordering here, right?
No, sir, but let's say like in T1, T2, you can have like time ordering function is A, B or B, A based on whether T1 is greater than T2 or T2 is greater than T1.
It doesn't matter. It is in a specific, because T1, T2, and T2, T4 are specific numbers, right? So it doesn't matter because the time ordering symbol will automatically order them according to the order of time. So, okay, there are two possibilities. Okay, wait a second. So of course, here there are two possibilities, there are four possibilities, but all of these possibilities are not realized together, right? Because you have to give, for this thing to make sense, you have to specify what T1, T2, T3, T4 are. And when you specify, there is only one possible ordering. It's a unique ordering, right? Are you following that?
Yes. Got it.
Okay, so it's not like there are two terms here, there are two terms here. They're not like, it's not like that. There's only one term here. And each term would be relevant on. So there is only one term in here and only one term there, and the time ordering symbol would simply. So of course, when you write it, you say theta this and theta that, but the theta function simply means that there's only one realization. Okay, so either only one of these terms will actually contribute, right? So there's only one. Therefore we do not have any extra thing. So now what we could do, we can here put the time ordering of ht1 to htn and ht tilde 1 to ht tilde m. Okay, that is what we can do here. Okay, because we can remove the time ordering because it's already taken care. And now we can do another trick is that, so here for this T1 to Tn, it runs from T2 to T1, and here from T tilde 1 to T tilde m, it runs from T3 to T2, right? That is what it runs from. But then I could just take all of them to T3 to T1, right? Because it doesn't matter, because the time ordering symbol again would take care of it. Or okay, wait, maybe what I can do is to, okay, put it in a different way. Okay, so yeah, okay, there's another way to see it. Let us try to do it this way. Okay, no, before that I have to take another step. Maybe that's maybe a better one to do. Is to so here this n and m are just running separately from 0 to infinity, right? What I can do, I can think of this in this following way, that I can rewrite the, okay, I can rewrite some nm is equal to 0 to infinity minus I to the power n by factorial n h bar to the power n minus I to the power m by factorial n h bar to the power m, as factorial, say, capital N is equal to, okay, maybe I should not use capitals. Let me use P. P is equal to 0 to infinity. And what am I doing is I first, okay, I will explain this once after. Let me write it first. Sorry. Okay, so what have I done here is as follows, that look, so this here, the sum, it is unrestricted. So what am I doing? I'm first restricting the sum of n plus n to be p, okay? And then after that, I'm taking this thing, minus I to the power p factorial, taking that out. And we only remember that p is equal to n plus n is equal to, p is equal to n plus n will contribute. So now this factorial p will get cancelled, and I will end up with the same term. So I'm just rewriting this in this way. It's the same thing, but I'm just first summing over n plus m with summing over n and m by keeping the n plus m fixed, and then summing over the p from 0 to infinity, right? And this object is nothing but p cn, right? So is that I'm just choosing n of them, right? If I look in this way, then you see that what I can do, I can simply now rewrite this object as dtp, and then I can take all of these integrals from t3 to t1, and then take the time ordering ht1 to htp altogether. Do you see why? Because why? Because here you see there are n of these, and here there are m of these. And now I'm doing the sum in a different way. I'm just choosing n plus m together, and then n of them are here. So now I have to basically partition them into two pieces. One piece is simply going from T3 to T2, and then T2 to T1, right? But this is an artificial separation, because I can just, because that is anyway should always be true. Because okay, there is a possibility that this set m is 0, that all of these things lie in the interval, this thing, T2 to T1. Here, all of this h lie actually between the interval T. So essentially this is like a partition So one way to do it, about is that this is nothing but a if I partition this thing into two sets, where a set of t's lie in this interval t1 to t2, and a set of t's that lie in the interval t2 to t3. But then I'm summing over all of these possibilities. So therefore, this factorial, this combinatorial factor is coming, PCN, and then that's simply a partition. But then you see here, but there are exactly as many terms here as they are there, because you see that if I'm simply this is simply a rearrangement of this thing, nothing more. Okay. So therefore, now what I can do is yeah, I'm doing, maybe I did something. Wait a second, what am I done here? Now I did something weird. What did I do wrong? Yeah, I think what I should do is, okay, wait a second. No, what I've done is, okay, no, what I have, okay, no, what I, okay, let me correct myself. Let me correct myself. No, what I did was a little bit stupid. Let me correct myself. So what I should do is to have to first start from here. Wait. Let me do this. So what I wrote this as an identity is correct, but what I should do is to start now from ut1 t3 and write this as sum I is equal to 0 to infinity minus I to the power p by h bar to the power p and factorial p, and then dt1 to dtp, all of these going from t3 to t1, and then t of ht1 to htp. Okay. Now what I should do is to use this identity, right? Because okay, this identity, the proof of this. Wait a second. Yeah. What? Sorry. I think I, okay. No, here I should have written. Okay. Let me forget this part. Okay. Well, I'm sorry. Let me forget this thing. This is. I should, yeah, okay, I wanted to write in that other context. Sorry, and then now here, when I write this, what I can do, I can further say that now out of this P, I will partition this T1 TP into two parts. A part of them would lie in the interval T1 to T2, and a part of them lies in the interval T2 to T3, right? It's an arbitrary partitioning. So what I will, this I can always do, right, without loss of generality. Are you following? So I start from this expression. I start from this expression, and I say that what I'm going to do, I'm going to, so without loss of generality, there will be part of them. So n of them here, and then p minus n of them here. Okay, that I can always do. And when I do that, what I have to do, I have to simply rewrite this in this way: minus I to the power p by h bar to the power p times p factorial. And then here I should write some n is equal to 0 to p, right? And then factorial p, factorial n, maybe n minus m, n minus p factorial, right? And then I would do the following times then dt1 to dtn of this from, as I said, from t2 to t1, each of them from t2 to t1, and then the remaining ones, dt tilde 1 to dt tilde p minus n, these all should go from t3 to t2, and then I could then break it up into this sum of two factorials, right? htn, and then t of h t tilde 1 to h of t tilde n minus p. So what I've done is simply rewritten this whole expression in this way, right? And now I note the following, that I could also done the following: n minus p, I should have replaced it by m, And then I could have simply put a delta P n plus m here. And then I could have summed from nm. Nm goes from 0 to P, both, right? And then this should be m, and then this should be m. And now I can remove the restrictor summation. So this is nothing but equal to what I can do now. I can forget, because here P is equal to n plus m contributes. This thing I can replace now by sum n is equal to 0 to infinity, sum m is equal to 0 to infinity, minus I to the power n plus m by h bar to the power n plus m, factorial n, factorial m. And then you see that when you combine these two, this becomes essentially u t1 t2 and u t2 t3, because now I can take each of these factors in front of these separate expressions and it becomes that. So you are going to submit this, okay, at some point by writing it up clearly in the proof. So basically what I've used, which I already wrote, was as follows, that sum over n is equal to 0 to infinity minus I to the power n by factorial n by h bar to the power n. Sum m is equal to 0 to infinity minus I to the power m by factorial n h bar to the power m. This is equal to sum p is equal to 0 to infinity minus I to the power p factorial p h bar to the power p, and sum nm is equal to 0 to p minus, sorry, simply factorial p by factorial n factorial m delta p n plus m. So I've used this identity here, right? That's what I did. And then this is a trick, okay? So just go through the video once after when I upload it on YouTube. And then once you go through this video, you should be able to rewrite the proof in your own way and submit it, okay? So as I said, that even those people who are auditing the course have to submit assignments.
So,
it's a good thing that,
so
yeah.
What do you mean by like rewrite the proof? Like basically have to write the same thing, right?
Yeah, write it clearly, that's all. Okay. All right, so that completes the first thing, right? And here you see that what we need to show is U dagger. Okay, so first of all, you have to prove that U is an unitary operator, right? So for that, you have this I h bar del by del t u t t prime is equal to h t times u t t prime, right? And now if I take a Hermitian conjugate of that, I should get minus I h bar del by del t u dagger of t t prime, right? Becomes u dagger t t prime times h hat of t. Okay. So let us try to see what happens to I h bar del by del t of u t t prime and u dagger t t prime. Okay, let us see what happens to that. So first I take the time derivative here. I would get ht times u t t prime. Okay, maybe I should do it this way. Okay, I can do it either way, but let me do it this way. U dagger u first. Okay, and then I first, okay, if I first take the derivative here, I take the derivative here, I get u dagger t t prime times h t u t t prime, and when I take the derivative here, I get the same thing but with a minus sign. Right? And therefore this must vanish. So it shows you that u dagger t t prime is a is independent of t, right? So this is t independent, but we also know that t prime is equal to identity, and u dagger t prime also should be identity. So it implies that u t prime times u dagger t prime has to be equal to identity as well. Okay. Is this clear or not? So
Yes.
this is independent of t, and I could put t is equal to t prime to see what the value is, and the value turns out to be 1, trivially. So it turns out then u is a unitary operator. So that's how you can see it, right? And then you have to show that ut t prime and ut prime t is also equal to identity, right? But here it might look a little tricky because here t is greater than t prime, and here t prime is less than t, right? So here you're going backwards. But then you see that what you could do is as follows, that so let us take this expression that we already have, right? U t1 t2, this is equal to dt. Maybe I should then write as d tau 1 to d tau n. Okay, I have to first write this minus. Okay, I'll just sum n is equal to 0 to infinity minus I to the power n by factorial n h bar to the power n d tau 1 to d tau n, and this goes from t2 to t1 and time ordered of h tau 1 to h tau n, right? So this, if I have to take u dagger of this t1, t2, what is going to happen? So all of these is going to simply become n is equal to 0 to infinity, but then I to the power n by factorial n h bar to the power n, because I'm taking the dagger here. And these integrals would be going again from the same d tau n from t2 to t1, the same kind of thing, t2 to t1. So now, and this, if I take the Hermitian conjugate of a time ordering, and all of these are Hermitian operators, so this becomes simply anti-time ordering, right? Because what is time ordering? Okay, so suppose I'm taking time ordering of two operators, two Hermitian operators, AT1, BT2, and without loss of generality, we can say that T1 is greater than T2, right? I mean, you can always take the other case. So in that case, it would be AT1, BT2. Now, if I take the dagger of this, or if you want, I take the dagger outside. So this is equal to then BT2, AT1, and this is exactly the anti-time ordering, where I place the anti-time ordering is opposite of time ordering, where you place whatever happens earlier, later. Sorry, what you pick, okay, here T1 is greater than T2. So whatever is earlier comes later, but in the anti-time ordering, whatever is earlier will come earlier too. So then this is equal to AT1 BT2, right? And we assume T1 is greater than T2, you can then take T2 greater than T1 and you get exactly the same conclusion. So therefore, that Hermitian adjoint of this is simply, that joint of this is simply anti-time ordering. Okay. Yeah, but you see that I can do a further trick, that here I have I to the power n and d tau. So so we have n of these integrals. Now, if I change the order of these integrals, it goes from T1 to T2, right? Suppose now I make it go from T1 instead of T. So here T1 was greater than T2, but suppose I take the other way around, I make it go from T2 to T1, then I get a minus sign with each of them, which I can absorb here. Okay. And now you see the time ordering is, this is what becomes something like time contour ordering, because here the time goes from T1 to T2, but the tau is actually is you can think of how it is ordered in tau. So one way to think about it is that you have, okay. So, okay, let me. So instead of thinking of it as time, you can think of some contour variable. And here the contour variable is increasing, and tau1 is equal to simply T1 plus, let me see, tau1 times T2 minus T1. So whenever tau increases, you go from T1 to T2. Okay, so 0 to, so here tau would go from 0 to 1, right? If tau is 0, it is T1, and if tau is 1, it is T2. So then all of these would go from, all these tau variables go from 0 to 1. And in this case, if I change this variable, so all of them go from, say, and this is something we can do generally always, right? Whatever your T1 and T2 are. And then this, you can replace this, because anti-time ordering is nothing but the contour ordering. When you're simply going around this time contour, right? So this is always true. So you see that, so one of the things that you could see that you can always write u T1, T2, whether T1 is greater than T2 or T2 is greater than T1, it doesn't matter. I choose a time variable tau I. Tau I goes from T1 plus tau I, T2 minus Ti. T2 minus T1, I can always write this as sum n is equal to 0 to infinity minus I to the power n by, minus I to the power factorial n by h bar to the power n. And then I can take all my tau1s to go from 0 to 1. And then I have the same contour ordering now, h tau1 to h tau n. This is true irrespective of whether T1 is greater than T2 or T2 is greater than T1, right? And if I do it this way, it is also easy to see, irrespective of whether T2 is greater than T1 or T1 is greater than T2, you always get U1, T2, U T2, T3 is equal to U of T1, T3. Irrespective of whether, you can do the same exercise again and see that. And therefore, you know that U T1, T2 times U T2, T1 it has to be equal to U T1, T1, but this is equal to identity. But we also know that U T1, T2 times U dagger T1, T2, or U dagger T1, T2 is equal to identity. So it follows that U dagger T1, T2 also has to be equal to U of T2, T1. So you could just think about it, and you should just write it up in a nice note and submit it, all of these properties. So the main point is as follows, that yeah, the main point of the exercise is as follows, that it is you could just work with U, and the U dagger is simply the U running in the reverse way. And this is something that we have seen earlier. So one pictorial way of seeing this as follows is, this is U going from, say, T1 to T2, right? And this is U dagger, or U going back from T2 to T1, that is same as U dagger. So this is equal to identity, and they exactly cancel out, right? So if there is no operator insertion and it's the same Hamiltonian on this side and that side, it's important it has to be the same Hamiltonian on this. So U is always with respect to some Hamiltonian, right? And this is the same Hamiltonian on this side, then this should simply cancel out. However, if I'm going forward using one Hamiltonian and going backward using another Hamiltonian, then they will not cancel out, okay? Then this is not going to be identity. But as long they are with the same Hamiltonian, they simply cancel out. Okay, so this is something that to keep in mind. So these were the exercises that you are supposed to do. So let me stop sharing and go back to the notes. How do I stop sharing? Okay, stop broadcasting. Okay, very good. So now where are we? Okay, so this is what we had to we have gone through these things now. So now what in this part, what we are trying to do, we are trying to do the following thing. We are trying to relate the time evolution using two different Hamiltonians. Okay, this is going to be very important for us for various to understand the physical meaning of different things. So often when you go to quantum field theory textbooks, they will introduce all of these time ordered operators, the commutators, but only much later they tell you what are the physical meaning of this of these things. So as you say that, so often, but in the quantum field theory books, what they do is as follows. So basically, you are trying to compute operator evolutions of operators in time, because that's all quantum field theory is about, right? So you measure the observables now, you see what are the observables later. That's all quantum field theory is about. But time evolution with a very complicated Hamiltonian is difficult. So what we want to do is to rewrite the time evolution in terms of one Hamiltonian as time evolution in terms of the another Hamiltonian. So basically, okay, in quantum field theory textbooks, they see that, the quantum field theory textbooks, they say that you're going to something like Heisenberg picture to the interaction picture. But actually what they mean is, what it actually implies is that the two different Hamiltonians evolving, basically is Heisenberg picture using two different Hamiltonians. If you use the Heisenberg picture using one Hamiltonian, that becomes easy to compute things. If you use the Heisenberg picture in terms of another Hamiltonian, it becomes harder to compute things, but you want to relate the two computations. So what we will do is that we first do, so quantum field theory textbooks to tell you that, okay, first let us convert to the evolution in terms of the free Hamiltonian, and then we can use Wick's theorem to compute everything. So that is why what we'll be getting at, but I'm just turning it a little bit around and first say, but the main point to keep in mind is that this is very general, that you have two arbitrary different Hamiltonians, H and H naught, and the physical meaning, and to understand the physical meaning, it's better to do it this way. Then let us keep, so H naught is arbitrary, not necessarily the free Hamiltonian or anything. It can be whatever you like, and H of t is also whatever you like, and they're differed by some extra delta H, right? And that's always, and what we are doing here is to go from, is to basically rewrite this Hamiltonian in terms of the other one. And the first step is this. The first step, I think, is very similar to, this step is very similar to what I just explained when I was doing that. So there were two Hamiltonians, and here what I'm doing is that H is equal to H naught plus delta H, right? What I'm doing is rather simple. I'm just splitting, so I can, when I take this to the power n, I have to do this binomial factor, n plus r factorial by n factorial r factorial. I'm just simply using a plus b to the power n would be n plus r factorial, factorial n factorial r, and part of this would be H naught and part of this would be delta H. But you see, I don't need to take care of the orderings here because time ordering is going to order them anyway. And all of these now go for the, it's not exactly the same what I did here, but very similar. Okay, so is there any question now about this step? If not, please ask.
Yes,
sorry, one by one.
Go on. Sure.
Yeah, who is going to speak?
Okay. Okay. I'll go. So here by time ordering. So like for like when I don't know how to put it. So here H naught and delta H happens like at the same time, right? So what exactly does time ordering?
No. Of course, H and delta H has. So for each of this, when I take H plus delta H to the power n, right? Sorry, it's not to the power n, this is H. So look, yeah, you can think of this as each of them should be H, right? So each is H naught plus delta H, okay?
Yeah.
So now I get how many factors I should get. I can choose either H naught or H and open it up, right?
Yeah.
Now, when I open it up, then I have to do a factorial. So how many out of this n tn's, I would choose some of them to be equal to, so okay, here it should be n plus r, that is, so suppose this n plus r. So first I should rewrite this n plus r. And out of this n plus r h, I choose n of them to be h0 and the rest of them to be delta h. That's all. You see what I mean? So h you open up, and then if you write this, and then you will get this factor n plus r factorial, and this will cancel with this n plus r factorial, because this is actually n plus r. That's what I said. The first step would be to rewrite this as n goes to n plus r.
Right.
And then you will get this overall factor of 1 over n plus factorial r here times this. So it becomes the same factor here. And this gives you this part. Okay.
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 Right.
So from where this combinatorial factor, due to the time ordering it comes, or
No, there's nothing to do. This combinatorial factor has nothing to do with time ordering. Again, let me explain. So this is HTN, right? Each of this H you should replace by H0 plus delta H. Are you able to see my arrow, this cursor?
yes, sir.
On the screen? Okay, so each of this H you are going to replace by H0 plus delta H. And now I'm opening this up, right? And when I open this up, I will get either H0 or delta H. And I choose, say, there n plus r of this. So n of them should be H0 and remaining r as delta H. And then the time ordering is simply going to sort it. Under time ordering, everything commutes. Okay. Okay. This is another thing. Under time ordering symbol, AT1 BT2 will be the same as AT2 BT1. Or sorry, under time order, AT BT prime would be the same as BT prime AT, because time ordering is going to order them along the time. So under the time ordering symbol, everything commutes. Right. It's simply a trivial thing. It's nothing. There's nothing very fancy here. It simply comes from the fact that time ordering is going to order everything under time. So on the time ordering symbol, everything will commute. So here the ordering will not matter, the way I'm writing these objects. Is it clear now?
Yes, sir.
Okay. Then this is the derivative. So then after this, what I do is I now open up this time ordering further, right? I open up the time ordering further, and then I get these kind of things. Okay, so d tau 1, dt 0, and so this step is clear to everybody. Have people followed this? So what
Yes,
I'm
sir.
going to do is,
I didn't get this, sir.
okay, so let us go through this again. No. So what is going to happen is, out of this n, I'm choosing n0, so again, I'm now dividing n into r plus 1 factors, because the r plus 1, that there are these delta h's that appear, right? Now, what is this delta h? Delta h is simply gbt times O hat p, and these are in the Schrodinger picture, right? These are in the I mean, they are not, there are some fixed objects. So, but now what I can do is that I can place n0 of them. So I'm just saying that out of this n's, I can split them into r plus 1 parts. n0 of them occurs before tau 1, and then like that in this way. Okay. I think, and then among this, yeah, so that's all I've done here. Okay. Is this clear now? What, at least this step is clear? Who was asking this? Again, Priyanka, was it you?
Yes, sir.
Okay, now is it clear? Or not?
Yes, sir.
Okay, so that's what I've done. I've just unfolded this time ordering by saying that let's assume that n0 of them are before tau 1, n1 of them are after this, and things like that. So that's what I've done here. And then I've placed this into, so this is, in the previous class, I was confused about this, how to place these integrations around, but now I've been able to fix it. So firstly, all of these proofs are not given in any textbook. It's usually, in some other textbooks, they give a part of this in a different way. But I think it's useful to see this I mean, it's there in textbooks, but not in this form maybe, because I'm doing it in a different way, that's all. Okay, so then you see that all of these are now ordered in the proper way. And then I would get a combinatorial factor here, because I had to choose n0, n1 out of the total n. And therefore, this extra combinatorial factor is simply, this factor is simply the combinatorial factor of dividing n into r plus 1 subsets of N0, N1, and NR, right? So that is what extra factor. And now these two will cancel out. Factorial N cancels out. Now what I did was I simply used this. This is exactly what I said before, a generalization of that. So this is simply rewriting this restricted sums as unrestricted sums. That's it. Because because this combinator, you can now, it's very simple to see. And once I do that, I can take these elements, this factorial N0 element in front of this, and all of these are going from, say, tau1 to t. So therefore, I can replace these terms into simply ut tau1. And then similarly, each of these terms becomes this. So now you see, you get a beautiful relation that this time evolution using h is essentially the time evolution using h naught, but then these operators are inserted in between, and there's overall factorial r because, yeah, there is a possibility of this overall factorial because of fact you can interchange them, and then you have this different insertions in between. So it's a beautiful thing actually, you see, but now what I could do, I could again use this trick which I just said, that like all of these things I can now convert to the Heisenberg picture, because you see what I can do, I can further split ut1 tau1 tau2 to first tau1 to tau0 and tau0 to tau2. Now tau0 to tau2 is exactly, yeah, so tau0 to tau2 exactly is u dagger of t0 tau2, and this becomes, so this becomes the Heisenberg picture because of this. And then this will, basically I'm just splitting this into two, and then each of them becomes simply the Heisenberg picture operators, but the Heisenberg picture with respect to which Hamiltonian? H naught, that's very important. And then you have an appendage here. But this appendage can be just simply taken out because it is not featuring in the integrals. And so this has the time, the t is simply appearing here, but nowhere here. So you can just simply take it out. And then you get this nice expression, which I said, that you dagger.
So why did you restore the time ordering? I didn't understand that. Like there was no time ordering in equation 10, but then you put it in equation 13.
Okay. So
I didn't understand
because
that.
it's, yeah, this is already time ordered, you see, because it's occurring in sequence. The t0 tau and then tau. This is,
so it's a trivial operation or something, or because it's already time ordered.
So basically, so here I couldn't have written the time order. I could have written simply this, but but then I'm replacing all of these integrals from t0 to t, you see, and therefore
they were already t0 to t. They were always from t0 to t, right? So you did not change any integral limits. So why do you need time ordering? Because all of them are
maybe uniform. Yeah, I'm sorry. I think this I should have. Oh no. So this is wrong. Sorry. Thanks for pointing this out. This integrals should have not gone from t0 to t. They should have gone from. Yeah, because these. Oh, sorry.
T0 to tau something. T0 to tau1, T0 to tau2.
Exactly.
Like
this should have gone from T0. This should have gone from. This should have kept the original stuff here. Like tau1 goes from tau2 to t, and tau r nr goes from t0 to tau r. So I think you should have. I should have done that. I think. I will correct this in the notes. But anyway, but the main point is so this is so
the final expression is correct. Like the equation 13, I think is correct.
The final expression is correct. Okay, so I'll just correct this, and then you see these are time ordered because they are appearing in the time ordered thing anyway. Because you see that this OB is at time tau1, right? When I replace it by the Heisenberg picture, but tau1 is greater than tau2, greater than tau. So it's already time ordered here, and therefore I can trivially replace the time order symbol, right? Because they're already time. But then I can make it unrestricted from t0 to t. Okay, so maybe I have to just make this small change here, and then you would become u tilde u. But what I'm going to do right now is to give a simpler proof of this expression. Okay, just two-line proof of this expression. I mean, actually, what I will give a proof of this expression now, u dagger u tilde, and in just 2 lines. But okay, the reason I went to this tortuous thing is simply because it's good to see once how to work with this complicated stuff. This is not what is usually done in textbooks, but you can also do it. But sometimes it's useful because in some other contexts, it becomes useful to see all this complicated operator algebra and get comfortable with it. So what I will do, I will try to give, but before that, let us come to the physical interpretation, which I gave earlier. So I think one simple thing is to say that you can always add some constant to the Hamiltonian. The ground state energy is 0. And so you say that the ground state, but there are certain systems where the ground state that doesn't exist a ground state at all. And but this kind of subtraction is a little bit ill-defined in quantum field theory, though. In quantum field theory, the ground state energy could be infinite also, and it doesn't matter. But physically, you don't see that, right? Physically, you only see excitations above the ground state. But in principle, it should not be infinite because.
Are you talking about vacuum energy or something, or?
Yeah, I'm talking of the vacuum energy. So in principle, any energy can gravitate. So if the vacuum energy is allowed to gravitate, that is allowed to be a source of the gravitational field, then that amounts to giving an infinite cosmological constant. And if you know that one of the, so the cosmological constant is actually the worst prediction in physics, is 10 to the power 120 times larger than the actual observed value in the universe. That is something we'll come back to later. So, but anyway, so, but suppose this constant is finite.
Finally, does gravity contribute, like vacuum energy contribute to gravity, or we just ignore the contribution of vacuum energy to gravity?
So that only a theory of quantum gravity can tell you, right? I mean, the answer to this question cannot be answered in only semi-classical quantum gravity. Let's come to this issue later. We'll talk about it at some point, okay? When we actually do quantum field theory. I mean, we are still doing quantum field theory, but we will see that. But the only difference right now, I'm pretending that you could put it to 0, the ground state, by adding a finite constant. And if you're able to do that, then this is simply the vacuum is invariant under time translation. Even there is no phase factor. And then when you take the expectation value of this guy, right? So you will have to take the expectation value here of U dagger, but that becomes 0. And sorry, not 0, it just gives you G back. And therefore, this simply gives you this, right? If I take the expectation value on both sides of this equation. And so therefore, so now you see there is a very nice physical interpretation of the time-ordered correlation function. So the ground state expectation value of the time-ordered correlation function is that you first evolve the ground state using this new Hamiltonian. So what you could say is that let this be like delta functions, like localized only at some specific time instance. And these are sources coupling to some specific operators. I evolve from the ground state using this new protocol. I just use the usual Hamiltonian, but then I give the short pulses, which couple to certain specific operators at certain time, and these are like delta function pulses. And then after that, I again see what when I go back to the whether I can go back to the ground state or not. I compute the time this amplitude, and the derivative of this amplitude with respect to the sources when the sources vanish are simply this, the time order, which simply means that you can unfold this in this way. The total when you unfold it, it becomes this is simply the integral version of this. If I integrate this equation with respect functionally with respect to sources, I simply get this, right? So it's basically it's an integrated version of this, the same object. And if I do differentiation, I get this. So basically, it has a very beautiful physical interpretation now. It's basically the change in the vacuum persistence amplitude is measured by the time-ordered correlation function. Okay. So what we will see, there's an analog of this for S matrices. You can have an in state and arbitrary out state here. When we talk about S matrices, we'll talk about this, and this would be like the time order. And in fact, this has actually such a beautiful expression that we will see that you can actually compute all the S matrices from this time ordered correlation functions. This is what is known as in literature as sorry, what is it called now? I'm getting this LSZ reduction formula. So that's what we will see. There's a nice formula called LSZ reduction formula that any kind of transition amplitudes can be computed from the time ordered correlation functions. But it's very important that you see that when I take this, these O's are in the with respect to the unperturbed Hamiltonian. That doesn't mean, okay. So here it's with respect to here, assume that H0 is time independent, but H0 can also be time dependent in many contexts. So it is essentially it's still so here it's in the Heisenberg picture with respect to the old Hamiltonian. And then taking this new Hamiltonian, taking its derivative when the sources vanish. So when the old Hamiltonian is actually new is actually the old, because when the sources vanish, H it becomes old. So this is a very important physical thing to keep in mind. Okay, it will come back to this. So the reason I'm doing this here in now, because you already get a physical understanding of what we are talking about, right? Before I start talking about, but usually in many textbooks is done in the reverse order. Only at the even many cases, many textbooks don't even unravel the physical meaning of these objects. If you read Weinberg or some other more modern textbooks, at some point they reveal the meaning of these objects, but much later after they develop the calculation tools and things like that. But I'm trying to do it in a bit reverse way because I think it's more meaningful today to do it that way. So when many of the times these books were written, you have to keep in mind, they had particle physicists in mind, and they wanted to train particle physicists to shut up and calculate all these different transition amplitudes, S matrices. But I think this era of shut up and calculate has now ended, and we should try to be a little bit, we can also try to look things in a very different way. And okay, so, all right. Now comes the physical interpretation of the commutator, okay? So this is something that I think I worked out. So essentially, here what you take the picture that you have the old Hamiltonian, and this perturbation involves a single coupling to a single operator B, right, like this. And now what I want to see how this expectation value of A has changed. So I'm measuring the expectation value at some time after I switch on this perturbation. So it has to be a causal response. After I switch on this perturbation, I measure the expectation value of A after some time. And I'm interested in the difference between the expectation values of A if I evolve under this Hamiltonian versus this. So basically what I want to compute the response of expectation value of A to perturbation by B, okay? So now what I'm doing, I'm taking this and writing this is simply the first step. If I look here, this expression, if I look at this expression, right, U tilde is equal to this, and I take the first term will be 1, the second term would be simply what I wrote, right? There's only one single B, okay? Is this clear? And then there's order G square. So now what I do, if I take dagger of this, I get this, that's obvious. I simply take the dagger of this. And again, I have done the same trick, yeah, it becomes plus. Actually, I have not done any further trick. And now what I want to compute is delta AT. So I need to compute this object. So basically I need to cancel out this 1 because that is, so if I just take the 1, it will give me simply A of T, expectation value of AT, but I'm interested. So I just want to subtract this out and look at what, so this will come only from this and this, but this comes before and this comes after. So you see that, so here A should multiply U times this, right? U times A should multiply. So I'm just taking U tilde now. I'm taking U tilde, I'm substituting U times this factor, and U dagger, I should substitute this times this factor, right? But I'm subtracting out the 1. So I'm just taking this part, I'm writing the order G piece here and order G piece here. So I get 2 terms, and A hat is sometimes sandwiched in between. When I substitute this, I get U times this factor. When I substitute in U dagger, I get this times this factor. So you see in the first term, I get U times this factor. In the second time, I get with the opposite sign because here the sign changes, and I get this times this factor, okay? But now you see U dagger A hat is nothing but it's in the Heisenberg representation with respect to the old Hamiltonian, and it is at time t, right? So this is nothing but A H naught t. And similarly, this also is nothing but A H naught t, okay? So this is also A H naught t, this is also here. So then this becomes a commutator, because now I can remove the tau here because it's again it's at t and it's not inside this integration range. So it becomes this, and now I can remove this restriction t naught. So now I can simply also replace it by theta t minus tau and remove this restriction on tau up to t. I can also take it to infinity if I like, and because of this theta function, it takes value when t is greater than tau. So this is often called the retarded correlation function, because by definition, the retarded correlation function is, this is a source and this is a change in the response. This is a response. Then this is nothing but the expectation value of the commutator. So this actually has a very lot of implications as follows. So what is the meaning of the commutator is that you first perturb the system with respect to some with respect to a source that couples to this B operator, and you see the response in the measurement of A. And that is what is the physical meaning of the commutator is. And this is, you can measure the commutator, okay? So, and remember, in both cases, you are in the Heisenberg picture with respect to the old Hamiltonian. So this is a very important thing. So this old Hamiltonian could be actually the physical Hamiltonian. So this need not be, so later when you go, and this is the reason why I'm doing this here, even without talking of the more practical point of view of computations, because here H naught is actual physical Hamiltonian and not necessarily the free Hamiltonian. So this H naught could be the actual physical Hamiltonian, right? Because here is delta H is simply a perturbation on top of whatever the Hamiltonian is. So this is a very important thing to keep in mind. And why? Because so actually I can remove this H naught here and just use the arbitrary Heisenberg picture because H naught was chosen to be an arbitrary Hamiltonian. So in quantum field theory, what you see is as follows. Suppose you do a perturbation B, it cannot affect the measurement of any operator outside the light cone of this point, right? And now this suppose the operator is localized at X. So it means that outside of the light cone, all commutators should vanish, right? So this would be actually the meaning of causality. So causality would imply that that the expectation value, or sorry, not the commutator as an operator identity should vanish, because the expectation value is in all states vanish. So it means that the commutator should vanish as an operator identity if the two observables are located at distances which are space-like.
Sir, but the integral 24 goes from T0 to infinity. So like basically at when the source is at tau is equal to infinity, even then that is having
because here there will be wait. So here in quantum field there should be an additional X index, the additional position index.
Okay.
Yeah, and so and here also you will have an additional position index.
Some tau minus something should be there. So like retarded function.
Okay, I will give you a better. So here, of course, you will have a position index on top, because the way to think about it is that, okay, I think I should have written as GABA, some indices here, and that then everything would have gone through, and these indices are position index. So I'm going to write this expression now in quantum field theory soon. So so just hold on your question. I think, but sort of it should be kind of clear from what I said. So here, so then here also there should be position indices, but the position indices are trivial. The point here is simply that as long as the measurement is outside, right, and this commutator should have, and this commutator vanishes, you don't see a response. So here there's a position index. As long as these two are outside, if this vanishes, you will not see a response. And this has to vanish in all states, right? Because the response also has to vanish in all states. So this must be vanishing as an operator identity. That's the main point. But the thing is that the time ordered correlation function need not vanish outside the light cone, because time ordered correlation function is not really a response function. So you have to know what is the final state you're looking at, right? And then you're saying the change in the amplitude, transition amplitude from here to here due to this evolution. And this is not actually a causal measurement, because you have to already know what is going to happen in the future, and you are not actually asking a causal question. So an analog of it is, I don't know if you are going to, when you are going to study GR, you will see something like that. Okay, let me come back to this things at the end of today's lecture again. So what I'm going to do now, so for the moment you have a physical picture, right, of this. What I'm going to do now, I'm just going to give a very simple 2-line proof of this identity, which I did not rather tortuous way for very good reasons, for us to be comfortable with this operator manipulations. I'm going to give a 2-line proof of equation 14. Okay. Now, so let me go back to my notes, my pen and pencil thing. Okay, so let me go back to my pen and pencil stuff. So what we want to do is to get an equation for u dagger tt prime and u tilde tt prime, right? So let us call this object vtt prime, just to give it a name for the moment. And what I'm interested is to compute minus IH bar del by del t of vtt prime. So if I do that, so what I have to do, I have to first, okay, then I have to take the time derivative here and then the time derivative there. If I take a time derivative here, I know I get minus, because u dagger tt prime, and this is with respect to the old Hamiltonian, right? So this would be h naught t, and then u tilde tt prime. And then I would take a time derivative of the u tilde. So I get u dagger tt prime. And then here I get the new Hamiltonian h hat t u tt prime. So it's obvious, it becomes minus. So now I can combine these two, and h minus h naught is delta h, right? So now we recall that h is to h naught plus delta h t, there's a time dependence. So this becomes equal to then u dagger tt prime delta h t, and then I have u tt prime. Sorry, there's a u tilde tt prime. But this I can rewrite in this way: u dagger tt prime delta ht, and then u tt prime again, and then u dagger u tilde, right? But this is nothing but v itself. So here I just simply inserted u dagger here, and u dagger u tilde is v itself, right? That's the definition of v itself. U dagger u is v. So I just included u dagger here, and then I get this. Now, what is this object? This object is delta h, but in the Heisenberg picture with respect to h0. And at time t, and then v t t prime. This object is, see, delta ht, okay, there's a t dependence, but this t dependence comes from the dependence of the sources on time, but not on the operators on time. The operators were still in the if you go back to the, so if you remember, delta H was written in this way. All delta H was written as sum B and sum GBT times OB, right? So these operators were not evolving in time. This were in Schrodinger picture, but now they're evolving in this way, but with respect to H0, the old Hamiltonian. So the upshot is as follows, that if I take all of these together, I get minus IH bar del by del T of V T T prime is equal to delta H H0 T. So this thing is in the Heisenberg picture with respect to the old Hamiltonian, and then you have V T T prime. Now you can do a similar trick, right? I mean, remember that you can then convert this, and now you can also say that when V T prime is equal to identity, that's obvious because if I take, because separately both U and U dagger goes to identity when T is equal to T prime. So V T T prime is also equal to identity. And now you can convert this differential equation into an integral equation. So which means that V T T prime would be equal to identity minus, sorry, this was IH bar, and I am stupid. Sorry. Yeah. So yeah. Yeah. Okay. I just wrote an extra minus sign. So then this should be equal to 1 minus IH bar, and then this thing I can rewrite as d tau, and then tau goes from T prime to T, and then I have delta H tau times U, or sorry, V tau T prime, but now this H is in the Heisenberg picture with respect to H0. And now using the very similar trick, you can now export this, you can simply, you just follow the same derivation that I did earlier to compute this time ordered, the time evolution operator. It simply implies that VTT prime is equal to sum over n is equal to 0 to infinity minus, sorry, there's I by H bar, okay, sorry. Minus I to the power n by factorial n H bar to the power n, and then d tau 1 to d tau n. It goes from T prime to T, T prime to T, and then I have a time ordered product of delta H, and with respect to H0, tau 1 to delta H H0 tau n. Okay. And now if I rewrite this in terms of the sources, which I have here, right, I get the equation that I wrote in the equation 14. So you have, so this is simply a sum over B, and I simply rewrite explicitly what this H0 is. So if you wish, I can rewrite it again. So if I substitute that, it will become sum is equal to n0 to infinity minus I to the power n factorial n H bar to the power n sum B1 to sum Bn, and then d tau 1 to d tau n. All of these go from T prime to T, and GB1 tau 1 to GBN tau n, and time ordered of OB1. But now with respect to this H0, T tau 1 to OBN. Now it's in the Heisenberg picture with respect to H0, T tau n. So this is exactly the equation 14 which I wrote down. I simply rewrite what delta H is here, and I get this, okay? And so it's a very simple, like 2-line kind of derivation, right? But which I did it a little bit more convoluted way earlier. I admit it was convoluted, but for a good reason, just to get us used to this operator kind of manipulations, which will be actually useful for us much later when we try to prove the Weeks theorem and many other things. By the way, the proof of Weeks theorem is hardly given in many textbooks, which I will give you actually more deep kind of query. So that is the reason why I'm trying to start with quantum mechanics, because many of these concepts are already there. The meaning of the commutators, the meaning of these objects are the same in any quantum mechanics. And in field theory, all the things that we get is that these indices B1 will also stand for spatial locations, because operators are labeled by spatial locations in field theory. So then you would get, so all of these integrals will simply become integrals over space, these summations. So anyway, so this is what we are. So you see that I have a very simple proof here, right? Now this actually has a practical meaning, and this is a practical meaning is what we are after. So suppose now you want to compute, now physically what we want to do, physically we want to compute time ordered products of O1 tau 1 to On tau n, where these are all in the Heisenberg picture, where Oi tau I are in the Heisenberg picture, with respect to the actual physical Hamiltonian.
Sir, and the actual physical Hamiltonian itself is also time dependent.
It could
Because
be, it need not
G
be.
of
It
t,
could,
I mean, G of t is.
in case of particle physics, no, right?
Okay.
But even in particle physics, there's some assumption of time dependence. So the assumption is that, I'll tell you where the assumption comes from. The assumption simply comes from that in the far, so you're basically everything is made of wave packets that come together and come out. So you can adiabatically switch on the interactions and adiabatically turn them off. I mean, that of course is a fiction. Actually, it happens naturally. But this is some mild assumptions that you have to put in, even in the case of, but you can think of like a material, right? You're subjecting material to some laser fields or something like that. So actually what we're interested, say, in transition amplitudes or something else. So this is sort of, so you already have some physical meaning of it. So when I said that okay, just, so basically this would be the starting point of many of computing a lot of physical stuff, and including transition amplitudes. Now, what you're interested in is actually the time ordered product. That this is an operator. This is not a matrix element. It's an operator. But you can also think of matrix elements, say, with respect to the vacuum or with respect to ground state. And then it actually becomes the seed for computing transition elements. We'll actually see how it works in a specific example, the harmonic oscillator in quantum mechanics. So in that case, you can actually compute any arbitrary transition amplitudes between one harmonic oscillator state to another, and where you are driving the system by anything. But basically the idea is as follows, that we are interested to compute this, where that this is in the actual physical Hamiltonian. I will come back to this. I will come back to this again later, very soon. But now the question is that, but this is hard. But the point is, this is hard. So what I do is I evolve with H0, not H. And I assume okay, something of that kind. Okay, here you can have time dependence or not, doesn't matter. I mean, everything can be time dependent here. This is not very important for us, this time dependence. So okay. So what I do is I evolve using this Hamiltonian H0 and not using this, right? And then I can compute, I'll also assume, and compute in perturbation series in GIT. So these, if these are small, what I can do, I can expand in this couplings and I can compute this systematically. So that's the basic idea. So what I do is that I want to convert. So what I want to do basically, so all of these O1 is in the H Hamiltonian thing. ON is again in the same H. I want to rewrite them in terms of Hamiltonian of H naught. Of course, when I do this rewriting, if I have n products here, I will get infinite such terms, right? But I still want to do that. So how do I do that? The question is, how is it possible? Okay. So the way we proceed is as follows. So first, let us try to see. Let us see that suppose some operator is in the Heisenberg picture with respect to the Hamiltonian H. Okay. So what it is actually. So this is nothing but, let us call it U tilde, okay? Just to distinguish, so U would be with respect to H naught and U tilde will be respect to H, okay? So just use this notation and it will be U tilde TT prime or TT naught O U TT naught, where T naught is a time and preparing the state or starting observations. So that's when all pictures agree, right? And this is U tilde, sorry. So what I can do is I can rewrite this again as U tilde TT naught dagger U TT naught and then U dagger TT naught, right? O hat and U TT naught U dagger TT. So I'm just writing identity as U dagger, identity as U dagger, U dagger again, and U tilde TT naught. But what is this object U tilde? And this is nothing but our VTT naught, right? That's what we defined a time ago. And this object is also nothing but is V dagger TT naught, is simply a dagger of this object. And the rest, which is here, this actually is the Heisenberg, is O hat in the Heisenberg picture with respect to H naught. So this is equal to V dagger TT naught times O in the Heisenberg picture with respect to H naught times V TT naught. So to summarize, OH T, where H is in the Heisenberg picture with respect to H, is nothing but V dagger TT naught So for this reason, often this operator V is called the time evolution operator in the interaction picture. So, but what it means is as follows, that the V is simply the operator. V is what you need to convert anything that is in the Heisenberg picture with respect to H to anything that is in the Heisenberg picture with respect to H naught. And from now on, I'm going to drop the T dependence in H and H naught. It's sort of understood. Because for the moment, you can have the T dependence, it doesn't matter. Okay, is this clear? So now what I'm going to do, I'm going to do the following thing. I'm going to now redo what I showed earlier, but now in this language. So basically, I can say that this is equal to. So what I'm doing here, I'm taking from T naught and again going back to T naught because V is a time evolution operator. I can interpret as a time evolution operator in the interaction picture, going from T naught to T, and then V dagger would be the time so you see that whatever appears later should have occurred earlier on the time contour. So it's like I'm going along this time contour here, right, from T naught to T, and then inserting this operator here, and then coming back. V dagger is basically back from T to T naught. So V dagger again, V dagger T naught is nothing but equal to VT naught, right? VT naught T. So here, basically, I'm going back. You can easily see that because it's simply a so that's very easy to see, because this U is the opposite of U dagger and U dagger is opposite of U, right? So that's then easy to see that that this is true. It follows simply from the properties of U. It then goes back to V, right? So what I'm saying is V is equal to U dagger U tilde, and V dagger is U tilde dagger, right? So now each of these arguments are revised, so it becomes nothing but V. So you can easily prove this from what we did with U, that V dagger TT naught is nothing but VT naught T, right? So, all right. So now you see, I can rewrite this. So this is a very nice picture, and this is often, this kind of diagrams are often called the Keldysh-Schwinger diagrams, or Schwinger-Keldysh diagram, or I would say contour. So this time contour, which goes from T naught to T and backwards, is often called the Schwinger-Keldysh contour. And it simply tells you that this is, for example, this diagram would mean that here this cross implies an operator insertion, but in the picture, in the actual picture T. So time evolution and the operators are in the same picture, okay, in this diagram. So the operator insertion here is in H naught, and the time evolution V is actually the time evolution. It's not in H naught, but the time evolution is essentially the time evolution operator interaction. That's the interpretation that I already said. So that kind of takes into account this. All right, so now suppose you want to do the following. I want to insert two operators. I'm sorry, I should start from H. What should I do? So this is something I can already now know. This is nothing but V dagger TT naught times 080 T, and then I have V TT naught, right? This is what OHT1 is. Sorry, I should have written T1 here, T1 here, T1 here. And then I'm writing OHT2, which is V dagger T2 T naught times 080 T2 and V T2 T naught. But you see, I can combine these two in a nice way. First of all, it's easy to see that V T1 T2 times V T2 T3 is also equal to V T1 T3. Okay, so let us see why it is so. Because V T1 T2 is nothing but U tilde U dagger. Oh, sorry, it's U dagger U tilde. Sorry. Yeah. So V TT naught is U tilde. U dagger T1 T2 times U tilde T1 T2, and V T2 T3 will be U dagger. Yeah, but okay. So I think I can, yeah, I can give you a more detailed proof here. But I think it's much easier to go back to this definition that I gave. Sorry, where was this proof that I did? I go back to this proof that I gave, right? And using this proof, okay, this is where, okay, no, this is the reason why I asked you to prove it in the alternative way. The reason I asked you to prove it in the alternative way, because now if you see this expression, if I have to prove that, though that expression here, it would take me more time. I can also do it in that way, but it's easier to see that if you you can now use the same proof that I gave for u t1 t2, u t2 t3 is equal to u t1 t3 by using the similar manipulations at this here. Now it is easy, much harder to do it in the other context, right? In this context here, because the V has no natural action on the states, but on the operator. Okay, so it is a bit harder to do it here, but using the similar techniques. So I don't want to do it using these things. I can also use this kind of techniques and prove it, but this will be a little bit harder. But the reason I gave, I went to the tortuous exercise in the beginning of the class instead of following the easier method that Kabir suggested, was that I can just simply repeat it here. Okay, so this is again exercise. Maybe you can solve this exercise instead of that, so that we have to submit this.
Sir, but rewriting in terms of U will not work here. Why won't it work? Like, we know identities with respect to U, and we can do the operator algebra required with U and prove it, right? Like, we're fairly comfortable with properties of U.
Yeah, you can also do it, or you can just simply redo all that we did in the beginning of the class of separating
the
this
integrals
into,
and everything.
Yeah, or separating this thing into two pieces where one lies between T1 and T2 and the other lies between T2 and T3, break it up and do the similar exercises to show it factorizes into two parts.
Yeah.
And these are all, it's the same, it's a very easy thing to do. Just follow the same routine that I did in the beginning. And then you can see all this expression because V has this expression written in this way. So then you could, but if you write in terms of U, it will be a little bit harder to show that U tilde. Okay, you can also show it that way. And there what you have to do, I can also tell you how to show it in terms of U tilde, is that you have to first go from infinity to minus infinity. This could, yeah, there's a nice trick that you can do there also. You can also try to prove it the other way, just by directly looking at expression in terms of U and U dagger, but it will be a little bit harder. But I think the more straightforward thing is just to look there, the exercise that I did. So this is exactly a repeat of the same exercise algebra that I did. Is it clear, Kabir, now? So simply go back to the time order product, sum over time order products, and then you'll see that. Okay.
Yes, sir.
Okay, so now if I do that, so you see that what happens here, you can also similarly show that V dagger T prime is nothing but V of T prime T. So using these two together, you see this is nothing but V of T1 to T2, right? So then the conclusion is that the time order product OH T1 and OH T2 is nothing but V dagger of T1 T0. Okay, and then you have OH T1, and then you go from VT1 T2 and OH T2, and then V of T2 T0. Okay, again, let us try to see it in a diagrammatic way. What is happening? So what is happening is, let me do it this way. So this is T2, this is T1, and then this is T0. So you see that I have to always go from, so as you see, I have to convert it to Urdu, as I said before. So I first go from T0 to T2. So this is V T0, T2 to T0. So I first go from T0 to T2. That is what V means, right? I go from T0 to T2, and then I insert this operator, which is in the Heisenberg picture with respect to H0 here, right, at T2, and then I go from T2 to T1. Then I go from, okay, then I turn back basically. But anyway, this and this would cancel out. So this is equal to identity if you wish. I can even go to infinity and come back, doesn't matter, because these two parts will cancel out, because as you said that this is equal to identity, right? And and then you come back from V, but V dagger T1 T0 is nothing but V of, I first start from T1 and go back to T0. Okay, so this is what it is diagrammatically. So does this tell you something? So what I claim is, okay, let's first try to rewrite. So this is the expression that I have, right? Okay, so what I'm going to now do is to write some, so I'll just put all of this in a very nice way and try to show you what's a calculational tool that what we need to do. So OHT is again this diagram. Sorry, it is V dagger TT naught, OH naught T, and V TT naught, right? So this is nothing but time. If I rewrite this, this is equal to sum n is equal to 0 to infinity minus I to the power n by factorial n. And let me call delta H T as equal to some V, okay? Just a short form. Delta H looks a little bit uncanny, and V is always in the interaction picture, or is in the Heisenberg picture with respect to H naught, Hamiltonian H naught. So this V dagger TT naught would be some minus I by H bar to the power n, and DT1 DTN. Maybe I should call it tau. D tau 1, D tau n, and time ordered of H, sorry, this V into H0 tau 1 to V H0 tau n. And then I put O H0 T. So this goes from T naught to T. Oh, sorry, I should have written T, wait, yeah, wait, I should have written I to the power n, and then this should have been T bar, okay? Because that is V dagger, right? I simply take the dagger of the expression that gives me V. And then this would be some m is equal to 0 to infinity, now minus I to the power m by factorial n, H bar to the power n. But now d tau 1, d tau m, which goes from T naught to T, now time ordered product of V tau 1 to tau m. Okay, I just simply unfolded this expression, and written this, okay? But now you see, using again similar kinds of tricks, this is an exercise and submit it. So submit this. It's again a rehash of everything that we did earlier, okay? So rehashing everything, you could again do the same kind of combinatorial tricks and now put all of this in a very nice and simple way. Okay, I will explain this notation, okay? Oh, sorry. Or okay. So let me explain what I've done. What I've done is I have written this integral as a closed time path. So therefore, there's a sign here. It goes from T0 to T and goes back from T to T0. So that's why it's a closed contour. That's why this is this sign here. It's a closed contour. And this symbol implies contour ordering, not time ordering. Okay. So one way to see it, it happens this way, because here you see it goes from T0 to T, but then this was I. What I can do, I can then reverse it from T to T0, then it will become, and this comes after this. So everything is contour ordered. So you see first this comes, and then this, right? And that exactly occurs in the contour. So first this occurs, this then happens, and this. So whatever appears later in the contour should appear later, and whatever appears earlier in the contour should appear earlier. So this is what, what I'm saying, the other way around. Whatever appears later in the contour should appear later. So this has occurred here. So that's the usual contour. So time ordering becomes contour ordering now, the same as time ordering, but except that time is replaced by the contour time. The usual time is replaced by the contour time. So here the contour time is tau, which goes from T0 to T and goes from T to T. And the operator insertion is here at time T. Okay, so which means that here I can reverse to get the contour ordering, I have to reverse this time ordering, but then I can absorb this with minus I. So that's why I only have minus I here. And then this operators are already ordered according to the contour. So I don't need to worry. And so I can simply replace everything under the contour ordering symbol, and it becomes this.
So could you write the definition of contour ordering? I didn't understand.
Okay, the contour ordering is very
like pictorially
simple.
it's clear, but the definition,
okay,
mathematical.
The definition of contour ordering is so tau1 and tau2 are the contour times, not the actual time. And if tau1 is after the tau2 in the contour, then you do this, or you do it otherwise.
The contour times you refer to the diagram you're talking about, right?
Yeah, let me finish then. Okay, so what I mean here is as follows, that so this is tau1 and this is tau2. Okay, so if I put it this way, the actual tau1, tau2 could be suppose this tau2. Okay, so this tau1, so this goes from T0 to T and T to T0. So this tau1, this tau2 could be actually greater than or greater. It doesn't matter. So it can be, if it's on the it's in the part of the contour that is going back, it's in the backward part of the contour. So this is the forward part of the contour, and this is the backward part of the contour. So this is a nice trick, because suppose I want to give an ordering where AT1 and BT2 always occur in this order, irrespective of whether T1 is greater than T2, right? What I should simply do is to put okay, sorry, it should be the other way around. Yeah, okay. So what I should do in this case, I should put always B here and A here, right? Because it doesn't matter whether what is actual values of T's, because this is inserted here and this is inserted here. So this tau1 and tau2 has two different things. One is a physical time, right? And whether it's on the backward part or in the forward part, right? It could be either inserted here or here. If I'm inserting it in the backward part,
the backward part time is always lesser than forward part time.
Exactly.
Even though physically they might be.
Yeah, exactly. That was my point. That was my point.
Okay.
This is something that is very useful, actually. You'll see later. So basically, it means that I can. So this is a definition of contour ordering. It only refers to where along the contour I'm inserting the operators, and this ordered according to it. It's a usual time ordering, but simply the real time is replaced by the contour time. That's all. Okay.
So in the contour you've drawn, tau2 contour is less than tau1 contour.
Yeah, because you see that I'm inserting A in the backward part, and this always appears later in the contour, so it will appear earlier, right? So first B operates and then A is operating. So this is tau2 and this is tau1. Now I should have written this way. So basically, A is then appearing later in the contour compared to B. Okay, that's what is happening here. Okay. Okay, I hope this is clear. Now, in this case, if you are putting any, so in this diagram that I drew earlier, you see that I have put both of these things on the in the forward contour. If I put both operators in the so if I put both operators in the forward contour, right? If I put both operators in the forward contour, then time ordering is the same as contour ordering. Okay. If I put one operator in the forward, one operator in the backward contour, then it's always ordered in a specific way, irrespective of what the physical times are. Now, why this is advantageous, right? Suppose I want to compute this object, right? AHT1, BHT2, where this is in the Heisenberg picture with respect to the actual physical Hamiltonian. I want to now convert it to, basically I want to convert it to in this way, H0T1, BH0T2 minus okay, let me write this maybe explicitly. This will become useful. So this is nothing but AHT1 times BHT2 minus minus BHT2 times AHT1, right? So now you see what I can do. Let me try to see it pictorially, what I can do here. So this is a very nice computation that I need to do. So if I want to compute, for example, the commutator, I want to find the response function, right? Using the actual physical Hamiltonian. So this is important for me to measure, say, the conductivity of a metal or viscosity of water. You see that this is very thermodynamics. This is going to be important. So this I can write in this way: HT1 BHT2 minus BHT2 HT1. Okay. Now this.
And there is a question in the chat.
What is the question? So this unitary output performs there. I don't know what you're asking, Atanu. Please try to stay with this. I mean, don't ask something that is ahead of. I don't know what you mean by Jacobi identity in this context. Sorry. Okay, so okay, so HT1 BHT2 minus this. So what I have to do is now, this is V dagger T1 T0, right? And then AHT1. Okay, so let me do it. Let me first write it and then put it into diagrams. What happened? I have no idea. What is this?
You zoomed into the
okay, sorry. Yeah. Okay, so this is VT1 T2 and BH0 T2 and then V T2 T0. Okay, and then minus of a similar expression. Okay. So now if I want to get this into a picture, you see, I have to always have this ahead of this. So let me put this into the first thing into a picture. I can actually now do the following trick. I can always go from t0 to infinity and then from infinity back to t0, because whatever I do, it should cancel out. I place this operator here. So you see here, A occurs first and then B occurs, right? Which means that I have to insert A. So this is T1 and this is T2. I have to insert A here and then B here. I have to insert A in the backward contour and B in the forward contour so that I always get this. And now in the other case, I have to take the subtraction where the opposite happens, right? In the opposite case, I have to insert A at T1 and B at T2. And all of these things are happening. So you see that these are going to cancel out, will become identity. And then this part, if they become identity, then this thing is always VT1, T2, right? Because you can always think that, okay, so according to the arrow, so V is always running from here to here. If I according to the arrow, right? So it follows the, okay, is it clear? So this is what I draw in pictures if I have to do it here. So this becomes, if you wish, I can rewrite this as sum t is equal to 0 to infinity.
Sir, so in the forward path, in the first term, the B should be in the second backward path or forward path.
Sorry.
So in the first term, the B operator should be.
No. So this is correct, right? This A is occurring later on the contour. So whatever occurs first on the contour should act first on the state. So this is going to be first, and then this is going to come, right? So what I wrote was correct, no? So yeah.
Okay.
And everything is in the Heisenberg picture with respect to H0.
So
Always in this time.
physical times T2 is less than T1 in the first, but it's opposite in the second. But T2 and T1 are fixed, right? Then how can you physically do this experiment?
Look, this is okay. First of all, okay. What do you mean by physically? I don't understand here. It's simply, as for the moment, I'm just simply doing some maths, and so here I'm talking of contour ordering, right?
Okay.
So this is what I'm going to now write. Okay, let me write this expression, and maybe then you will see. Minus I to the power p by factorial p h bar to the power p. And this is, again, the closed time contour, which goes from t0 to infinity and then comes back from infinity to 0. And then here I should have the contour ordering of VH0 tau 1 to VH0 tau p, and then AH0 T1, but this I'm inserting in the backward contour, and BH0 T2 I am inserting in the forward contour, okay? Right? And then a similar expression, right, where I just interchange the backward and forward contour. Minus TC okay. So this actually, all of these objects have physical interpretations, but so if I take A, B in a specific order, it actually has some physical interpretation, but there's not much time for me to uncover the physical interpretation of each and every ordering. But there is a fun thing that I can do maybe before, but for the moment, this is what I'm trying to say, that so if you want to compute, if you want to develop a computational tool, you have to make sure, you have to making sure, so you have to you have to know how to compute on this funny contour that goes back in time, right? That goes forward and then backward in time. So when you come to, so what we will later see when we only compute transition amplitudes, the backward part of the contour will simply dissociate. It will not be very important. But if you are trying to compute something like a transport coefficient, for example, the conductivity of a metal or viscosity of water, you actually need to do this computation. So basically what you have to do, we also learn how to do such computations in this course. So, but here we have to, make sure that, what people sometimes do is that, so this T1 and B together tells you where on the contour you are putting it, right? Because T1 can be either in the backward contour or in the forward contour. When you specify them together, you specify where in the contour it is, right? And similarly here. So you see that these two are the same. So all of here, the T1 is the same, is associated with A, and T2 associated with B, but what was backward becomes forward, what was forward becomes backward. Because only then I can reverse the ordering, right? And this becomes the commutator. Okay. So this is, well, what we will do is now, what you will see that we will now learn how to actually do these computations. And what we will do, we will simply convert this contour ordering in something called normal ordering, and that leads to easy computation. And this is what is going to be Wick's theorem. So we will use some H0, which allows to do some nice tricks, and then you get this interpretation in terms of Feynman diagrams. So we'll do all of these things, okay? But for the moment, all I'm trying to say is, so this is how we want to do. This is the way we proceed. So the main point is that we want to compute everything in the Heisenberg representation with respect to some operator H, because as I said, in quantum field theory, everything is nothing but operator algebra. You don't talk about states, you only talk about operator algebra. So we start with, say, a commutation, but when you talk about Heisenberg picture, you have to actually specify the Hamiltonian, and this is H. So now I say this H is a small perturbation about H0, or some systematic perturbations about H0. So what I do, I convert this into this and this kind of expressions. So this expression minus something similar, and then rewrite it in this way. So so basically your task would be to exercise would be submit this, and also to submit, okay, where is it that I wrote in terms of 2? Yeah, also to submit, for example, this, yeah, submit this too, or try to see how this you can go from here to. Well, if you do that one, this also should be rather easy. So also submit this. So so I will send the exercises soon in some and put it as an assignment. It's not really an assignment, simply it's exercises. So do submit it next week, before Saturday next week. And this is very easy because it will take you just one. It will just take you just. So basically, what you do is simply go to this lecture and write it out in a nice way. That's all you need to do. Okay, is it clear now?
So time ordering is important with respect to the whole H0 plus delta H, because we want to calculate in and out states or something in the future. That's why we care about the time.
No, for the moment, no. For the moment, what we are interested to do for this specific computation that I said is not it's simply the same A expectation value of A, or some state psi, expectation value of AHT1, BHT2, right? This is what we are, and we already see what's the physical meaning of this. You simply, and in this case, T1 is greater than T2 always, physical time wise, right? And then we see how to, this expression that I wrote up is simply a way to compute it in terms of evolution, in terms of H0, which we can easily solve and compute.
Okay.
Okay. So this is, now physically we know what it means. Physically, this means that I perturb the Hamiltonian, actual Hamiltonian H. Now this is an actual Hamiltonian H, not H0. I'm perturbing by some g of t bh or bt or not. Okay, let me write it not clearly. So what's the physical meaning of this again? The physical meaning of this again is that I take h, h tilde now, which is h plus g of t times b, where g of t is equal to delta t minus t2 times some g naught. Okay, so I'm simply perturbating this Hamiltonian, and I'm seeing the response of A at time t1, right? And this is equal to nothing but this commutator multiplied by g naught. Because when I do the integration, because the delta function, it only contributes at one place, right? Because g is a delta function, you can go back to the expression. So it only picks up. So there was a tau here. And because g of tau has a delta function, so it only picks up here. So this commutator is the response of the measurement of A at time t1 when I perturb the original Hamiltonian, not the h naught, but h itself with this. But if I want to compute this, I cannot compute it in terms of h. I can only compute it in terms of h naught. So this becomes a perturbation series like that. So this is an expansion in various time order products, and each term in this expansion is something in the perturbation series. Okay, because h is equal to h naught plus some small perturbation, and these v's are this coupling constant small g's, or these extra perturbations. So V is like a small perturbation, and this is an expansion in V, if you like. Okay. So the first term you see is nothing but the commutator of A in the H0 itself. When all of these V's, none of these V's exist, because when you take P is equal to 0 term, the first term is nothing but simply this in the H0, right? But then you get a series of other terms, infinitely many. And we can compute in perturbation theory by using Wick's theorem. That is something we will see soon. So this is the basic idea of this, of how we compute such things in real life. So this is basically to set you up with the basic kind of computational tools for the moment. So in the next class we will continue from here, because what I want to now in the next class I will immediately tell you how these things is exactly the same expressions in quantum field theory, right? Except that these operators have a label, which is a spatial level. That's all. So we'll then come back to quantum field theory, make some comments on quantum field theory, and then we will go back to the quantum mechanics again. The reason we are doing it this way is that when you actually go to quantum field theory, you will see that you are getting confused with too many new concepts coming at the same time, and also a lot of new kind of computational tools. So what I want to do is that you first let us try to disentangle the computational tools and the physical meaning of each term at first, and then go back to quantum field theory, because then you can focus on the more concepts and not too much on the computational tools or what is going on. So there is a reason I'm doing this way. And what we are doing now is what is called Schwinger-Keldysh perturbation theory, because and this is called the Schwinger-Keldysh time contour. So, but before ending the lecture today, let me try to generalize what I just said. Suppose you want to compute the following thing. So an example is, I want to compute something like this. I take the ground state, I perturb AT1, BT2, right? And I take the ground state, and now I perturb it in the opposite order. I first perturb AT1, and then I perturb BT2. Sorry, what I should do is, I made a small mistake. So let us say that T1 is always greater than T2, okay? What I do, I first put the B perturbation and then put the A perturbation. And then I put the opposite thing. I first put the A perturbation and then I put the B perturbation. So you see that now the T1 is associated with B, and this is not the same what I did before, right? Where the T labels doesn't change, right? So let us call it psi1 and let us call it psi2. So what you can show is that this is something I don't have time, that this product, this inner product, psi1, psi2, is a measure of quantum chaos. Right, and essentially what happens is that this thing actually grows with time like this, and this is often called the Lyapunov exponent. Yeah, for small time. So this is often called the Lyapunov exponent, and yeah. So of course it's normalized, so this doesn't grow. This inner product cannot be without bound or something. So now how you want to compute such a thing? If you want to compute such a thing, you see that what you need to do is you need to actually have a contour of this form, which goes from T0 to infinity, infinity to T0, again like this, and then you want to put A, B like this. If you just use two contours, you cannot get this. So, okay, let me rewrite this in this way. So you see that if I take psi1, psi2, I can then see it is first BT2, AT1, and then I have AT2, BT1, right? The ground state and ground state. So this is equal to psi2, psi1, right? If I see it correctly, have I written it correctly? No, I haven't. So this is AB, which is correct, psi1. And if I take the dagger of this, it will become AB again. So then this should be, sorry, AT2, BT1. Because so you see that you have this AT2, BT1, AT1, BT2. You have this funny kind of ordering. So first if you see it along this contour, what you have to do, you have to go, whatever appears here should come later. So you have, you put A at T2, you put B at T1, then you put A at T1, and then B at T2, right? This is how you should order this. So you need this contour. You cannot just do it with a one folded contour, and you can draw similar. And then if you have this contour, so you see that all observables can be obtained by all kinds of orderings. If you have like 4 operators, for general ordering, you will need 4 folded contour. If you have n operators, you will need some, and each of these things means something actually. They correspond to some physical things. Like this funny thing corresponds to some quantum chaos. So if you look into like modern quantum field theory, and you see what modern quantum field theory research is about, you see people try to compute these things. They are not simply computing scattering amplitudes. So what we should do is to learn how to compute such things in this course. And this is very similar. It's not very harder than computing. But these are what is called in observables, because these are all related to something that comes back to itself. So this is a funny contour. This is something you can call generalized Schwinger-Keldysh contour. Okay, and these kind of observables. So there are many such observables, and for each correlation function has a physical meaning. Whatever ordering you put, it has some physical meaning. Often we know the physical meaning, often we do not, right? But there is some physical meaning. You should be able to ascribe to each and every such ordering. But now the point is that if you want to compute this thing, we have to relate everything to some H0 picture where we can do the computations, and then we have to use this kind of tricks which I mentioned. Okay, so that's all I want to say today, and that's all for today. Let me stop sharing.
So we have a class tomorrow or directly on Tuesday?
We have a class on Tuesday. Next class would be on Tuesday.
So nothing tomorrow.
Nothing
Yeah, okay.
tomorrow.
Okay.
Okay, so can we, from the next class, can we start at next Saturdays? Can we start at 9:30 a.m.? Because then we can, because today I took a long time. I didn't realize I took 2 hours today. Sorry. But anyway, so the next, so if I start at 9:30, I will not try to, I'll try not to go over time. But today it took long time because I had to switch between this and that and things like that. Okay, so all right. So sorry for that. So maybe next time we can start from 9:30. 9:30 will be fine for you guys.
So 9:30 to 11. Sorry,
9:30 to
yeah.
11. Yeah. Is it better?
Okay. Yeah.
Yes.
Okay. All right then. So that's all for today. See you on Tuesday.
You will upload the assignment or?
Yeah, I will also upload this assignment.
Do you have any other like piece of notes which summarizes the things that extra things that you said today? Like it's not